For nearly a century, our understanding of cosmic destiny was governed by a single titanic force, gravity. It was the universe's great architect and its eventual executioner. From the moment Edwin Hubble revealed in 1929 that distant galaxies were fleeing from us, the script for the future seemed written. The universe was expanding, yes, but it was an expansion fighting against the relentless inward pull of every star, every galaxy, every wisp of dark matter. The cosmic story was supposed to be one of two endings. Either gravity would eventually win, pulling everything back together in a cataclysmic big crunch, or the expansion would coast forever, slowing but never stopping, fading into a cold, dark, empty big freeze. The only question was which it would be. Then came 1998. The High-Z Supernova Search Team and the Supernova Cosmology Project, two rival groups of astronomers, published data that shattered this entire paradigm. They were using a specific type of stellar explosion, a type Ia supernova, as cosmic lighthouses. These supernova are what we call standard candles. Because they all detonate with nearly the same intrinsic brightness, their apparent dimness from our perspective tells us precisely how far away they are. By measuring their redshift, the stretching of their light as they race away from us, we can calculate the speed of their recession. The goal was simple: to measure the rate at which the universe's expansion was slowing down. But the data that came back from telescopes like the Hubble and the Keck Observatory was utterly, profoundly wrong. The most distant supernova, the one showing us the universe as it was billions of years ago, were significantly dimmer than they should have been. They weren't just farther away than expected, they were much, much farther. This could only mean one thing. In the time it took their light to reach us, the expansion of the universe hadn't been slowing down. It had been speeding up. This wasn't a minor correction. This was the equivalent of throwing a ball into the air and watching it accelerate into orbit. The discovery, which would earn its leaders the 2011 Nobel Prize in Physics, implied the existence of a new dominant force in the cosmos, an anti-gravitational pressure woven into the fabric of space-time itself. It was a phantom, an entity we couldn't see or touch, yet it accounted for nearly 70% of the total energy density of the universe. We gave it a name as mysterious as its nature: dark energy. This wasn't just a new entry in the cosmic ledger. It was a fundamental rewriting of the laws of physics on the largest scales. It resurrected an idea Albert Einstein had once called his biggest blunder: the cosmological constant, a fudge factor he'd added to his equations to force a static universe, only to discard it when Hubble proved the universe was expanding. Now it seemed something like it was real, and it was in control. The implications were staggering. If this force was constant, the universe was destined for an eternal, accelerating expansion, a future where every galaxy beyond our local group would eventually be pushed beyond our cosmic horizon, their light forever unable to reach us, leaving our descendants in a cold, lonely island universe. But this raises a far more unsettling question. We've assumed this dark energy is a benign, constant property of the vacuum. But what if it's not? What if its behavior is more complex, more dynamic? The standard model of cosmology, the lambda CDM model, treats dark energy as a simple cosmological constant, lambda. It's neat, it fits the data we have, but it's also an admission of ignorance. We have no fundamental theory that explains why the vacuum should have this specific non-zero energy value. In fact, our best attempts using quantum field theory predict a value for this vacuum energy that is 120 orders of magnitude larger than what we observe, the single worst theoretical prediction in the history of physics. This colossal discrepancy suggests we are missing something fundamental about reality. It whispers that dark energy might not be a constant at all. It might be a field, something that can change over time, something with a hidden nature. We are adrift in a cosmic ocean, powered by a current that makes up 70% of everything, and we have absolutely no idea what it is or how it truly behaves. Every model of our universe's future is built on an assumption about this unknown. So we must ask, what if our assumption is wrong? What if this invisible entity, this force that mocks gravity and dictates the fate of the cosmos, isn't just an expansion engine, but a built-in traitor, quietly dissolving the very foundations of reality from within? From that unsettling acceleration emerges a question that cuts to the heart of cosmic existence. What, precisely, dark energy? To grapple with its identity, cosmologists use a critical parameter known as the equation of state, represented by the letter W. This simple variable describes the ratio of dark energy's pressure to its energy density. It is the key that could unlock the universe's ultimate fate. If W equals -1 exactly, then dark energy is Einstein's cosmological constant, a constant, unchanging energy density of empty space. As the universe expands, more space is created, and with it, more dark energy, driving a smooth, eternal acceleration. This leads to the Big Freeze or heat death, a future of profound isolation and cold. If W is greater than -1, we are in the realm of quintessence, a dynamic field whose energy density could decrease over time, potentially even allowing gravity to retake control. But there is a third, far more terrifying possibility, one that lurks on the very edge of our observational data, a possibility that is consistent with our current measurements, even if it feels physically impossible. What if W is then -1? This is the domain of phantom energy, and it leads not to a slow fade, but to a violent, finite end. In a universe dominated by phantom energy, the rules are grotesquely inverted. As space expands, the density of this phantom energy doesn't just stay constant. This creates a horrifying positive feedback loop. More expansion creates more phantom energy, which in turn creates an even more violent expansion, which creates even more phantom energy, and so on. The repulsive force of dark energy grows infinitely, unstoppably, until it can overcome every other force in nature. This is the foundation of the Big Rip hypothesis, first proposed in a 2003 paper by Robert Caldwell, Mark Kamiankowski, and Nevin Weinberg. It's a detailed step-by-step timeline for the complete and total annihilation of all structure, the unmaking of existence itself. According to their model, if W is, for example, -1.5, the end would come in approximately 22 billion years. The first signs would be subtle. Billions of years from now, the repulsive force would become strong enough to overcome the gravity binding galactic clusters. The Virgo supercluster, our cosmic home, would dissolve. Then, roughly 60 million years before the end, the force would overwhelm the gravity holding individual galaxies together. The Milky Way would be torn apart, its spiral arms flung into the void, its stars becoming lonely wanderers in an ever-expanding darkness. The escalation from there is brutally swift. About 3 months before the final moment, the phantom energy would become more powerful than the gravity holding our solar system together. The Earth and other planets would be ripped from their orbits, flung into interstellar space. With just 30 minutes left on the cosmic clock, the Sun itself and every other star would lose its battle with gravity and explode. The Earth, now a cold, dead rock hurtling through the dark, would disintegrate. In the final seconds, the onslaught targets the very building blocks of matter. The electromagnetic force, which binds atoms and molecules, is next to fall. The planet's fragments, the very rocks and dust, would be atomized. With a mere 10 to the minus 19 seconds to go, a fraction of a second so small it's almost meaningless, the strong nuclear force, the most powerful force we know, the glue that holds atomic nuclei together, would be overpowered. Every atom in the universe would be ionized, their nuclei shattered into a spray of protons and neutrons. But the rip doesn't stop there. In the final infinitesimal moment, the phantom energy would become infinitely dense. Not even protons and neutrons could survive. They would be ripped apart into their constituent quarks and gluons. The very fabric of space-time would tear, culminating in a singularity of infinite scale factor, where all distance becomes meaningless. It's a universe not just ending, but unmaking itself, atom by fundamental atom. This isn't just a theory of cosmic destruction. It's a chilling whisper of reality's ultimate vulnerability, a testament to the fact that the same force driving the majestic expansion of the cosmos could be the very traitor that orchestrates its absolute undoing.